Sure, I'm glad to be here. I'm a professor in Cambridge, and I'm a computer scientist. And the AI for Energy team asked me to come here to give you a little bit of sense of where we're going in terms of some of the frontier research and the moonshots we're looking at. I work in the David Attenborough building in the Cambridge Conservation Initiative. That's not Boris Johnson, that is David Attenborough rappelling down to open the living wall in our building in Cambridge. And I've been doing this work with a ton of really generous ecologists and conservation scientists who've spent their time teaching computer scientists like myself and my group about what the interactions and challenges for nature are. So thank you very much to everyone involved. Now, the basic thing that we do is we try to take lots and lots of data from lots of different sources, and we try to glue together some very fragmented information. And the core challenge is that the data itself is in many different forms. So you might have observational data, you might have the results of randomized controlled trials, you might have camera traps in the ground or bioacoustics, and you might have lots of valuable data hidden in people's minds that might not be written down in traditional forms. And all of this is required to build a model of the world. And what I'm going to tell you about very quickly in the next few minutes is some of the generations of technologies we've built in the last 18 months. And to give you a sense of the pace of change, the cost of each of these technologies has dropped by 2 orders of magnitude since we started, and only one of these existed 18 months ago, and entire new fields of AI have come up that have made new things possible that I'll demonstrate to you as we kind of head down there. So I'll start by language models, which all of you have no doubt used through ChatGPT, and go into some of the more exotic stuff that is up and coming now as well. And I'll go through it quickly, but I'll be around for drinks afterwards to have a chat in more detail for anything you want to know more about. The basic loop that we work on when it comes to generating these AI systems is exactly what Shashin just described, where we want to process a lot of very diverse semi-structured data that is not in a clean form, and we drop all of this into a training process. And what we try to come up with are these foundation models that can be built once and then reused many times. And the crucial aspect of using this for any kind of nature-based purpose is that we don't just treat these as black boxes, we put humans in the loop, which means that anywhere where we're working in a spatially explicit way, the humans have the information at their fingertips in the form that they need in order to take a critical decision using an evidence-driven mechanism. So it's not just asking ChatGPT to tell you what happens, it's trying to provide a path through these complicated data sources to give you the insights that you need, and then running this in a continuous loop as the humans have questions. So this is the theory. In practice, what is happening is that there's lots of places where this might go wrong, and we call this the red pill, the bad use of AI. And what tends to happen is that if you feed on your own outputs, so that is, if we used AI-generated outputs as a source of our new information, then you end up kind of feeding on yourself and not having any more information, and this results in a collapse of these models. So imagine that we just constantly feed ourselves the results of ChatGPT, which is happening increasingly now as more and more academic papers, more maps and so on are generated using these systems, and this is a bad way to go, because we end up with black box systems that are increasingly feeding on the past and not predicting the future of a warming planet. So it's actually not very useful for predictive purposes. So what we want to do is to look at the positive, responsible AI side of this thing. So how do we build systems that are transparent, they keep track of their data that goes into these systems in order to let us unlock a few key things. First of all, we want to make sure that fieldwork continues to be invested in, because it's the only way we have of knowing whenever the AI models are wrong. AI models tend to work very well when you're within distribution, but as soon as you find the unexpected results that we always see in any kind of natural environment, you end up not being able to predict them. So fieldwork is essential for us to have the frontier of what is going on in the world, and then we use AI to help plug in the gaps for this year as opposed to trying to predict what might have happened a couple of years ago. And also, we want to capture original thoughts, that knowledge that is locked up in people's heads that isn't just a result of asking a statistical model, and continue to make sure that we can keep these original insights for humans as well as we can. And the reason for that is that we need to make hyperlocal predictions that are as accurate as possible for nature on the ground. So if you think about atmospheric predictions, it's like magic, right? You could just look at anywhere, any time in the world and predict what the weather is going to be. It's 3 variables. If instead you go into trying to predict these things on the ground, we have thousands and thousands of essential variables to decide exactly what is going to happen on an ecosystem, perhaps the size of the pond in your backyard. And so the order of magnitude complexity of doing these kind of predictions is high. So what we've been doing is, first of all, beginning with the evidence that we have, and then moving on to try to figure out how we can get more and more accurate in our predictions. So the first thing that we did was, when we began, was to ask ourselves, where do we currently get our evidence sources from? And the answer is that we often get a lot of evidence from the literature, from the scientific publications. So we went to Cambridge University to help our colleagues in conservation evidence, one of the founding partners of AI for Nature. And we said, well, could you give us your papers? And they said, well, which papers do you want? We're the Cambridge University libraries who have access to everything. And we said, yep, we'll just take it all. And so we downloaded about 50 million papers from digital sources. And it turns out that when you apply LLM technology to it, you don't ask it to understand these things, but you use it to augment human search. And so what you've just seen here is a visualization, first of all, of a 2-dimensional view of the world's literature, segmented into topics. And then you can see the giant richness of when you have these higher dimensional embeddings that you get from AI systems, where topics, the green represents something that was surveyed by a systematic review, and the gray blobs represent something that wasn't. And there are millions and millions of connections across things that are not obvious if you just do a simple keyword search. And so we use this to build a system that we call a living evidence database, where we can take a lot of the information from the academic metadata. We can then look for relevant papers for some inclusion criteria. Maybe we're trying to survey the state of butterflies and moths, or we're looking at corals. And we can drop down a bunch of relevant papers and dramatically speed up the rate at which experts in that particular field can do a systematic review. And along the way, this is not a black box. We can trace every single paper that's gone into it. We can reproduce the same results using consistent baselines. We can make sure they're accessible as long as the papers themselves are open, which is increasingly happening. And crucially, anyone else can come along and verify the same results. So this is an example of how we could use LLMs to unlock a vast amount of information to help users kind of speed up. But the problem is, you hit limits into what we've recorded. It's a bit like trying to explain to a child how the world works without letting the child ever go out into the world. So the next thing we did was develop a brand new foundation model that we've trained from scratch, so not based on language at all. What we did was we took satellites as the input, and we said, imagine if you are learning the world from the sky. We take 10 years worth of satellite data, and how can we come up with something that is as easy to use as a map, but in the style of a machine learning model? And so this is a view, a false color view of the world as seen from 8 years worth of satellite data for 2024. The colors don't mean anything, but they show that there's clearly some segmentation. What this Tessera model does, our new foundation model does, is that for every 10 meter squared part of the planet, it learns 128 numbers that represent some meaning and differentiator for that tile across the entire year. So it captures repeated observations using satellites, so about 150 observations per 10 meter squared tile. And it learns, instead of just 3 numbers, like red, green, and blue, it learns 128. And when you start to look at the structures of the things that it learns, without any labeling, it becomes a very, very rich kind of multidimensional structure. This, for example, is something we're using to try to map hedgehog highways across Cambridgeshire. This is Cambridgeshire, that's Cambridge down there. And as you can see, the colors have no meaning, but with these foundation models, you can train it on a bunch of downstream tasks very, very quickly, and reuse the same model multiple times, just like we do with LLMs, in order to do geospatial workflows very, very quickly. So some of the use cases that our collaborators are putting Tessera to is everything from land segmentation to canopy height estimation in tropical forests, to crop yield analysis anywhere in the world, including the seasonality of the crops, because this is captured in the model, all the way to higher level complicated tasks such as counterfactual difference analysis for carbon credits or biodiversity, and then even looking at degradation maps. So the key thing here is that, going back to the energy discussion earlier, that we can train one model, we generate embeddings for the whole planet from 2017 till 2025, and it becomes a very cheap process. It runs on my mobile phone to run many of these kind of downstream tasks. So this is something we're very excited about because it provides a new source of information that isn't just the literature. So this is a technology that kind of came up in the last year. I thought I'd show you, well, what's been happening in the last month. This is how quickly things are going. And there's something new up and coming called agentic AI. And this is some of the more advanced models that can not only learn from language, they can also use tools in order to manipulate the real world, and they can write source code. And it turns out that this is an amazing way of manipulating large amounts of data. So often in biodiversity, we use a GBIF database, and the GBIF database has been growing incredibly fast. It's a global biodiversity database for records and occurrences worldwide. And as you can see, there's about 4 billion records. Well, you can't see actually, but there's about 4 billion records, and it's growing near exponentially. Citizen science, all kinds of stuff is speeding it up. So what we thought was, how do we help the IUCN do their red list assessments? Because they have to assess the endangered species for lots of species, do it under pressure with lots and lots of data that is derived from places like GBIF. It's really hard to deal with 4 billion records when there's no kind of format in those records. So this is an example of something that was built in about 2 days using this new agentic AI. We said, instead of coding it from scratch, which might take a year, can we just describe what we're trying to do and get the AI to build a dashboard that is a complete dashboard that can manipulate this very complicated database. So you can see, for example, if we look into birds in this database, the number of years since birds are highly assessed. So there's been lots and lots of cases where the IUCN has repeatedly assessed these birds. So there's not many at all, in fact, beyond 10 years. So what if we wanted to find something that was a really bit, just a little bit different? Let's look at mammals. So I'm going to look at data deficient, so things that have very few records. I'm going to look at things that were last assessed over a decade ago. And then I'm going to sort this by the assessment date. And you can start to see here that we can see things that are been assessed 16 years ago. My internet's gone wrong. Let me just find one of them. So here, for example, we've got this elephant shrew, which is either a rodent or it's taxonomically challenged. No one's quite sure what it is. And you can see that it had just 3 records at assessment. And then there's been a number of records analyzed since then. And so what you can do here is you can very quickly, once I tell it I'm not an AI, you can tell I've been using this through my AI quite a bit, so it's justifiably suspicious of me. And so you can see here that there's just a very few records when the IUCN was analyzing what was going on. But then when we look at the records that have been analyzed since, there's lots more information coming up there as well. Oh, it's not coming up there. So what this is doing, while this is loading, so you can see here, for example, there's lots of observations from a naturalist, someone from observation.org, and they're all trying to kind of get a view on where this data is. So we can very quickly, for an assessor, navigate our way through billions of records and quickly kind of form the tailored views that they want to see without ever writing a line of code. But we're also not supplanting the original data sources. We're providing complicated tailored maps that kind of navigate their way through this. And we can actually generate these per species. So if there's something special you need to do, you can just kind of pull that off. So this is an example of how we can use agentic AI, not just to build one website, but to build a website per assessor that does exactly what they need in a hyper-specialized kind of way. So where is all of this going? It's going to be a crazy year. So we're seeing, first of all, a huge rate of change in the pace of AI. We're seeing that we can build tools that would have previously taken us a year or more to build in a matter of hours now. And so our challenge is really going to be one about discipline. How do we make sure that the data that we're outputting to the world has its provenance track so we know where it came from? So in a world where we can build almost anything that looks generative and is confidently incorrect, the systems we're building are a new breed of libraries where we want to keep track of the evidence going into the world, but we need to make sure that we can trace, reproduce, keep them accessible and equitable worldwide, and crucially make them verifiable by third parties so that we don't have to take any one organization's word as the final word. We're calling this a network of living evidence databases. not run by any one organization. Really, it's the roles of libraries in the modern world that have to act as this kind of data curator. But of course, libraries have to keep up with technology that's moving incredibly fast. We have growing pressures on development needs, as many of you here will know. And so ultimately, we have to make sure that we go back to the basics. We have to make sure that we can glue these things together to give you the kind of biodiversity data products at the resolution that you need to do your jobs, and to make sure that it's evidence-driven at the same time. So there's a lot of challenges going on there, but certainly my team of computer scientists is highly motivated to make sure we get to that bottom of evidence-based outputs, and a lot of the technologies we're developing are pointing in the right direction. They are being used for societally destructive purposes, but they can also be used, I think, to build a highly nature-positive future. So I'd be delighted to discuss some of the things you want to use this technology for afterwards, but for now, thank you very much for listening.